So last time we had the proportion of students who buy hard copies of textbooks, and the null was it is equal to 0.32, alternative not equal to 0.32. The claim was the alternative. We set an alpha of 0.25, so probability of typo error. We found the distribution. X happened to be 5, I believe, and X or B, the test statistic is 5, and N is 12. P hat will then be 5 over 12. Yes, it's 0.46. Clearly, P hat is not equal to 0.32. So one may argue, well, the claim is true, but we can't jump to a conclusion that defeats the purpose of statistics. Again, we have to account for randomness. So the value we set was 0.25, and we looked at both sides, kept on adding values. It came to 0.0242. Had I gone one more step, I would have exceeded 0.05. So the rejection region, this side doesn't matter. Just A, yes. And test statistic is 5. So clearly we do not reject none. So that makes sense. Now, p-value. For a two-tailed test, in the past 2023, you would have simply found the area about the test statistic and multiply it by 2. You cannot do that with a binomial, especially in this case. The only time we can multiply by 2 is when binomial is symmetric. So the only time we can use that trick or approach is when P0 is equal to 0.5. In other words, the distribution has to be symmetric. I'll show that using R as to what we're talking about. Now, how do we find the p-value? Since we are looking for an extreme event for a two-tailed test, we simply have to find all probabilities that are less than or equal to the probability of B equals X and add them all together. We have the probability summarized. So we just have to go up and look at all the values that are less than or equal to the probability of B equals X. Or the distribution equals, in this case, 5. So the probability of 5 happening is 0.1786. We could find significance if I could find outcomes or number of successes that are less likely than what we have. So 0 has a probability that is less than 0.1787. One has a probability that is less than 0.1787. Two has a probability that is less than 1787. 3 isn't, 4 isn't, 5 isn't, 6 is. And scroll down. 7, 8, 9, they all are. So 0.03957, 0.01164, 0.00243, 0.0003. The rest are small, so I'll just put 0. I could have put 0 for 0.0003 also. What do we get when we add all those values? I forgot that part. We have to do less than or equal to, so 0.1787. Now, what do we get? You round? Did you round it?
Yeah.
4 decimal places.
5386.
Okay. We have 0.5386, and that is the p-value. So if I conclude, ignore everything that we did, and I'll just reject them all and go with the alternative, the probability that I would be making a type 1 error is 53.86%. Should you make a conclusion knowing that the probability that you will be making an error is 53.86%? Is that smart? No, absolutely not. So do not reject the null. Same conclusion. Yes? Does that make sense? So it doesn't matter which approach you do, the conclusion has to be the same. That's one way to check your work on an exam. So what I want to show is a symmetric binomial and one that is not symmetric. So it doesn't matter what n I have, as long as the probability is 0.5, which is the probability of success. I would end up getting that curve. Would you agree that that is symmetric? So it doesn't matter what n I have. I could change that n to 24, that to 24. Of course, it is going to shift, but still, is that symmetric? Yes. But the moment I change, say, 0.5 to 0.32, which is what we have, no longer symmetric. Yes. In other words, one side is heavily weighted than the other side. Symmetric in the sense, right in the middle, 50-50 on either side. That's not the case here. Likewise, if I put as 1, 2, still, we can see a slight skew coming up. If I go toward 1, still I have a skew. Does that make sense? So the only time we can do multiplying by 2 is when we have p equals 0.5, but that's not what we are doing. So I've got to do this approach. Now, when you do the homework. R makes things easy. Now, to practice and understand this, you always use R. In R, the test that we use is binomial.test. And the syntax is very straightforward. It's asking for X, it's asking for N, it's asking for P, and the type of test. So I am going to type X, followed by N, which is 12 in our problem. What is P? 0.32. And P is our null value, not the P hat value that we have. And the alternative is two-sided. So if you perform a right-tailed test, you would type in greater. If you perform a left-tailed test, you type in less. And hit enter. Boom. Do you see the p-value up there? Can you see? Visible? No. What is the p-value? 0.5386. Isn't that what we had here? Yes. Now, the other two problems that we did, right and left hand, try it at home. It will match up. So our next order of business is to get to the confidence interval. Here, it tells us the proportion of students who buy a hard copy of textbooks would be between 0.1516 and 0.7233. If I kept collecting samples over and over again, 95% of the time, the true value will fall between those two numbers. Did 0.32 fall between, or does 0.32 fall between 0.15 and 0.72? That is an easy question. Yes. So in other words, the confidence interval contains the value 0.32. So there is a possibility that the proportion will equal 0.32. So you shouldn't be rejecting. No. Does that make sense? So you can easily determine whether to reject the null or not by obtaining a confidence interval for the most part. Okay? They are equivalent, a confidence interval and a two-tailed test. Clear? Which is Z. I wrote two versions, the P hat one and the one with B. Doesn't matter which one you use. So B minus N times P naught divided by square root of N times P naught times 1 minus P naught. That is the formula you would use if you're using the number of successes. We don't have to round in this case for B. So B is 5, N is 12, P naught is 0.32, divided by square root of 12 times 0.32 times 1 minus 0.32 is 0.68. Yes? So from earlier, that is the exact p-value. Now, large sample approximation, the standardized test statistic has a distribution. What is that distribution from last time?
Normal.
Normal. Mean 0, variance 1, or standard deviation 1. we want to find critical values. So in this case, where does the critical value lie? We're looking at a two-tailed test. There's one on the left, one on the right. And we want to find that number and that number. So if I find one, I can multiply by negative and get the other because the distribution is symmetric. That shaded area, what does that equal to? What did that equal to last time with a one-tailed test, right or left? I shaded on the right-hand side for a right-tailed test, left-hand side for a left-tailed test. Casey, right? Alpha. Alpha. So what's your name? Casey, right? So it is alpha, but since it is a two-tailed test, and if you go back to what we did with a binomial exact test, we took a bit on the right-hand side, bit on the left-hand side, made sure when we added, I got 0.05 or less. Since this is symmetric, I can equally divide on either side. So 0.025. Good. So the notation is just z sub alpha over 2. How did we find this value last time? Do we recall? So second mode to exit, second box will give us that list, and we have to pick inverse norm so that we could find a critical value, and we should always enter the area below. What is that area below on the left-hand side? It is 0.025. That gives me negative 1.96. If I find one, multiply by negative 1, I would get the other. So negative 1.96, positive 1.96. Where does the test statistic fall? 0.7179, it's right over here. Did the test statistic fall in the rejection region? No. Should we reject them all? No. We can find the approximate p-value using a normal approximation. Here, a normal distribution is symmetric. So it is 2 times the area above the absolute value of the test statistic. Now, even before you start that process, do you believe that the p-value is going to be bigger than alpha? Why, Connor?
Because you've already failed to reject more.
Well, no. I mean, using the picture. How would you explain why using this picture?
Your alpha is divided by 2, so it's already split in half. It's just not here.
Any other answer? One, test statistic falls here. 2, if I found the p-value, I'm going to find area above the absolute value of the test statistic, yes, which is right over here. That's going to be clearly bigger than 0.05. Yes, it's a huge area. So even before multiplying by 2, I have a huge probability. So when I multiply by 2, it's only going to get bigger. Yes? So how do we find that area, which is the area about the absolute value of the test statistic? Absolute value of 0.7179 is still 0.7179. So we do second first. We want to find the area above the standardized test statistic, which is B star. Your book calls it B star, but you can denote it as that also. So in terms of the notation, I believe I used C star alpha and B star alpha last time for the approximation, correct? So do make that change in terms of notation. The book uses B and C for exact tests. Right hand side is B, left hand side is C. For an approximate, it uses B star for right hand side, C star for left hand side. So 2 starts at B star, which is 0.7179, standardized test statistic. And the area keeps on going all the way up to infinity, comma, second comma, funky E, 99, mean 0, standard deviation 1. Good. Enter. I get 0.2364, but that's not a p-value yet because this is a two-tailed test. So we've got to multiply that by 2. So the approximate p-value happens to be 0.4728. Of course, you can't expect them to be the same. So given the approximate p-value 0.4728 and the previous one 0.5386, which one would you use? Should you use in practice if you encounter this scenario? Would you use the exact p-value or the approximate p-value? Exact. Why is that, Jimmy?
Just the most accurate one.
It's the most accurate one. So this is an approximation. This is okay if n is large, but when n is not large, then we have to use the exact test.